Okay, so the final exam is, I think it's your last final. It's on April 23rd. It's 2.5 hours long. In terms of content, your final exam will be cumulative, so all course material, but there'll be a strong emphasis, as you expect, placed on post-midterm content, which is modules 4 and 5. So the format will be, it'll look quite similar to your midterm exam in terms of these short answer, multiple choice questions, plus some long answer. And the style of questions will be pretty similar to the midterm as well. So you can expect some short answer, multiple choice theory questions and kind of light application questions. Then the long answer questions will be pretty similar to tutorials, homework, that sort of thing. So you have a lot of options, ways to practice for the final. So I'll give them kind of in order of what I would do if I was studying for your final. So I would look at the first thing I would do is I would look at the practice final. So I'm going to post that by next Monday. That'll be your best. So the practice final will be basically post midterm stuff. So I've already given you a practice midterm, so you can use that to practice your pre-midterm stuff. But post midterm stuff, I'd look at the practice final. Tutorial questions. So you might have noticed on the midterm, a lot of the questions are similar to tutorial questions with kind of an extra level of difficulty or something else you have to figure out how to work with based on course concepts. So I highly, highly recommend you go through the tutorials in the class. Any tutorials that you didn't really see right away or that you got wrong, or if you are comparing to your tutorial answer versus the solution and you see a discrepancy, definitely look at those. You also have a lot of homework assignments with practice problems in them. All those have solutions posted you can use. So I've given you the numbers there for pre and post midterm. The last thing I would do is the practice midterm. So oh, I'm sure most of you looked at that for the before the actual midterm you wrote. If you haven't, it's a great time also to look at that. The practice midterm will help you. The short answer questions will help give you an overview of the theory for the practice midterm. You can also look at your actual midterm too. It's not on that list, but any questions on your midterm that you got wrong will obviously be really valuable pre-midterm study information. So I'm going to hold office hours the day before your final at 2 to 4 p.m., but also around during the finals period. So if you want to have a meeting, you have any questions, just please let me know. I'm generally available during that time. Same with the TAs. Any questions on format, um, content, or how to study for the final? So a review of what we've actually covered in this class. So pre-midterm content, we had 3 modules on the midterm. One was on definitions, descriptions of fluid motion. So yeah, definitions, visualization, vocabulary, perspectives. Um, Module 2 is on forces in fluid motion. So we ended up getting to the Navier-Stokes equations, different types of forces in fluid motion. Module 3 was on non-dimensional analysis. So that's where we did Buckingham Pi, design of experiments. And we finished that off with a field trip. Modules 4 and 5 are the post-midterm content. So this is what the emphasis on your final is going to be on. So we only have 2 modules here. So one is Bernoulli's equation and how we extend that to internal flows. So these 2 modules are what I'm going to be reviewing today. Module 5 is on integral conservation laws. So at the end of that, we talked about Reynolds transport theorem, but we also showed you what the integral conservation of mass and momentum look like for a control volume. So I'm going to spend some time today going over just kind of key formulas and concepts from these 2 modules here. I'll have some more time to do this on Wednesday, and I hope to get to some important examples on Wednesday as well. Any questions? No? Okay. Okay. So yeah, key formulas and concepts. So we started off after the midterm looking at Bernoulli's equation. So Bernoulli's equation says that P plus 1/2 rho v squared plus rho gz is constant. Remember, this is like conservation of energy. Okay, so P is a flow, it's called flow energy, but you can think of it like a type of potential energy. So there's some analysis techniques that actually draw analogy between fluids and electrical circuits. So in that analogy, pressure is usually like a voltage, so it's a potential to create flow. 1/2 rho v squared is like a current, so it's the actual flow. So that's going to be kinetic energy. Rho gz is gravitational potential energy. Okay, so the sum of these three different types of energy is constant energy under the assumptions of Bernoulli's equation will just be exchanged between these three different types. So we also talked about static, dynamic, and stagnation pressure. I'll review what those are. So P is the static pressure. And static pressure is the actual thermodynamic pressure of the fluid. So that's when you look up in tables, that's what you're seeing is P in this equation. 1/2 rho v squared is the dynamic pressure. And rho gz is hydrostatic pressure. Okay. The sum of static and dynamic pressure gives us stagnation pressure. So that's P stag, P plus 1/2 rho v squared. And it's called stagnation pressure because that's the pressure that you get in the fluid if you suddenly bring it to a stop at any point in the fluid. So you convert all that potential and kinetic energy just into a pressure that's felt at a point. So I've stated the main point of Bernoulli's equation is that the sum of all these is constant, but that means we can actually link two different points together. So an alternate way to state is that P1 plus 1/2 rho V1 squared plus rho G Z1. It's the same variables, just at a different point, point 2. Okay. So sometimes Bernoulli's equation is stated like that. There's a common, I guess, mistake that we need to be aware of, and it's that Z is defined positive upwards here. So remember that this is the definition of Z in this equation. So it's positive upwards. Okay. Any questions or concepts you want me to focus on here? The assumptions behind Bernoulli's equation are really important. And there's something that I've emphasized quite a bit because they're very often broken without realizing that we're breaking one of these assumptions. So I guess, can anybody tell me one of the assumptions? Yep, Aaron? No external work? So what's an example of external work? Like a turbine or a fan or a pump or something. Okay. What's another one? Yep.
Steady state.
Steady state. So what does that mean if a flow is steady state? What does that mean about the three different types of lines we covered in pre-midterm? They're all the same, right? So if you say put a smoke visualization in a field that's steady state, you automatically draw the streamlines as well. So normally the smoke visualization is a streak line. Okay, so let's get steady state. Yep, did you? Along a streamline, okay. Good. So along a streamline means that this summation is constant only along a streamline. So in a flow, you might have these different streamlines that do this. This summation is only constant along one of those streamlines. So that means that in a fluid that satisfies these assumptions, streamlines are actually lines of constant energy. So if you go to a different streamline, there's possibly a total different energy. Okay, so there's anyone else? Yep, sure. You had your hand up first. So yeah. No viscous effects? Okay, that's good. Inviscid, nice. Yeah, inviscid. So no viscous effects. Remember that this energy equation is analogous to our sort of swinging pendulum, where a very idealized version of physics where we neglect friction. So viscous effects in a fluid just means friction. So just like we have a coefficient of friction that creates some sort of friction force, we have a viscous force in a fluid, and that coefficient of friction is kind of like viscosity. Okay. Um, yes, please. No heat transfer, right? So we didn't do this extension of Bernoulli's equation in this class, but it's an energy equation. So you can extend it to account for heat transfer. But the equation above, definitely no heat transfer. So fluids that get hot or cold, and there's energy exchange that way, can't be accounted for with the equation I've given above. Okay. Anything else? Yep. Incompressible flow, right? Okay, and when you think incompressible flow, what is the, I guess, characterizing property? What's the main thing that we think of with incompressible flow? You've answered a lot. Just think it in your head. AJ, yeah. Conservation of mass. So that would apply to any flow, right? That's kind of a law of physics, so it applies to any flow, right? Are you thinking of the divergence of the velocity field, the continuity equation? That's true. So definitely for incompressible flow, we have this. Okay. Is that what you were gonna say, Aaron? What were you gonna say? The Mach number? Okay. Yep. So these are all things that indicate possibly incompressible flow, but it's not really the definition. Yep. Is that what you're going to say? Constant density, right. So the important thing with incompressible flow is that rho is constant. So rho is constant actually leads to these things. So for an incompressible flow, the conservation of mass, like you said, is true. So continuity looks like this. We also know that we can generally assume incompressibility if the Mach number is less than 0.3. But the thing that really we should think about in incompressible flow is constant density. So that rho here is the same rho along the streamline, so incompressible. So in fact, that Mach number of 0.3 is actually derived from, you'll see this in incompressible flow. So when you look at the energy equation for an incompressible flow, it kind of looks like Bernoulli's equation, So if you take a Mach number difference between 2 points less than 0.3, you get something like a 10% error. So that's what we've deemed acceptable. So that's where that 0.3 comes from. You don't have to worry about that for this course. These are all very good that you guys are sort of tying these concepts to incompressible flow, but the constant density is the main thing for incompressible flow. Any other assumptions? No? Okay, good. Yeah, so there's 6. So as I mentioned before, a very strong hint, you will be asked for the assumptions behind Bernoulli's equation on the exam. So make sure you either know them, memorize them, and save some room on your formula sheet, or put them on your formula sheet. Speaking of the formula sheet, so I didn't mention that in the slides. So the formula sheet is also no restrictions for the final. It is double-sided too. So you get a double-sided, no restrictions formula sheet. For things you should include on there, you don't need to include the Buckingham pi theorem. You know that table that gives you kind of common units for the different variables in fluids? You don't need to include that on your formula sheet. So if you want, you can include it for reference. But it is highly unlikely I will ask a Buckingham pi theorem question on the final since I asked you one on your midterm. So that's the main use of that table. Okay. The other thing you don't need to include is you don't need to include the Moody chart. You don't need to include the roughnesses or loss coefficients, that sort of thing. I will provide that on the exam. So in the same way for the practice midterm, I'll give you a practice final that shows exactly what I'm going to provide on the exam, so you can figure out what else you need to provide on your formula sheet. You will need to provide things like the friction factor equation. And which friction factor equation did I say you should use for Hancock's and on tests and stuff like that? Holland equation, right? Good. Okay. Any questions on the formula sheets? Yeah. Okay. No. Yeah, don't worry about that. You don't have to put the massive table on Wikipedia on your formula sheet. I will just give those either as internal diameters, or I'll tell you things like the nominal and the wall, OD and the wall thickness or that sort of thing. Yeah, so you don't need to have the table of pipe schedules on there. Any other questions about the formula sheets? No. Okay. So that was basically Bernoulli's equation, the concepts. There's some good homework examples about different calculations you can do with that in terms of exchanging energy. The next thing we moved on to was internal flow. Okay, so internal flow, we know our mass flow rate. M dot is rho V average A. There's also a hydraulic diameter that we defined for AC over P. So AC is the cross-sectional area. And P is the perimeter. I'm going to give you a drawing for that just to make it clear. So if we have a box, and say this is a square duct or something, it's entirely filled with fluid. P is the perimeter of this, and AC is the cross-sectional area of this. So the hydraulic diameter, very conveniently for a circular cross-section, is just equal to the diameter of the circle. So dH equals D. We also defined our Reynolds number based on diameter. Rho V average D over mu. V average D over nu. So that's the same thing, and that's because recall that, sorry, nu is mu over rho. Okay. So we have some different criteria. So this Reynolds number, again, the Reynolds number almost, for many cases, in fact, the main purpose of the Reynolds number is to allow us to to detect how much turbulence is in the flow, how much inertial motion uh, dominates over viscous motion. So the top is kind of an inertial scale almost. So it's a velocity times a length scale. And the bottom is just kind of the viscosity. So it's a viscous scale. So if there's a lot of inertial motion, we expect turbulence. So remember the internal flow Reynolds number is different than the external flow Reynolds number. In general, for any sort of different fluid subproblem, there's likely going to be a Reynolds number defined for that specific case. And so people have studied and characterized these flows in terms of their Reynolds number. So the criteria will be different for each different case because the Reynolds number is defined on different variables for each different case. But the idea behind the Reynolds number is always the same. So Reynolds number based on diameter, less than about 2300 is laminar. It's between 2300 and about 4000. That's called transitional. If it's above 4000, then we can assume, sorry, I mixed up my color coding. If it's above 4000, then we can assume it's turbulent, fully turbulent. So these are some of the numbers that this was the, again, if you're interested in the history, this is the actual original Reynolds number. So these are the numbers that, Reynolds saw. Okay. So as I said, in most cases in the real world, we have fully turbulent flows. I'm sure as you saw for your project, the Reynolds numbers are commonly in the hundreds of thousands, if not millions for real world flows. So turbulence is a more complicated, definitely more complicated to deal with than laminar flow, but it's just kind of a reality of life when we do engineering fluid mechanics. Any questions on this Reynolds number, hydraulic diameter stuff? Before we get into the frictional losses and stuff like that, there's one more thing that we touched briefly on that I want to remind you about, and that's the entrance length. Does anyone kind of remember what the entrance length is or what it tells us? Yep. Yeah. How long until the boundary layer forms? Do you have a different answer, Aaron? Yeah, fully developed. So they're both kind of right. So the entrance length is the main engineering reason for the entrance length is that after the entrance length, you can assume that the velocity profile is constant along the pipe. It's not evolving anymore. And the reason that that happens is the connection of the boundary layers. Okay. So the entrance length for laminar flows, LH over D is 0.05 ID. And for turbulent flows, it's just roughly 10 diameters. These are very, very rough relations, but like for example, your project, your pipe is much longer than 10 diameters. So 10 diameters, if you have say a 30 centimeter pipe, 10 diameters is just 3 meters. So you very quickly become fully developed. So this entrance region is often not neglected. If there's something interesting happening in the entrance region, you can't analyze that with the Bernoulli's equation that we looked at because that assumes fully developed flow. You usually will have to do something like CFD or experimental tests and that sort of thing. Any questions about the entrance region? Yep.
What would be like you fully developing to a transition point?
Fully developing to a transitional flow? Yeah, so the transition just refers to, I guess, the stability or degree of turbulence in the pipe. So you still would have like the velocity profiles for a transitional flow are difficult to predict. But even for say a transitional flow, after it fully develops, you would sort of assume that the velocity profile is constant along the pipe. That's really tough to do for transitional flows. For the turbulent velocity profile I've given in the pipe, that's actually the average profile. So for transitional flows, that average is going to be much harder to predict, but you'll still have a point where it's kind of fully developed. So it doesn't evolve anymore along the length of the pipe. Um, but you're right. I haven't actually given the definition of the entrance length for a transitional flow. And I'll say just don't worry about it. It's way too problem specific. Okay. Any other questions? Yep. So we'll do the extended Bernoulli's equation now. Okay, so I'll give the two forms that we talked about in the class, which is P1 plus 1/2 alpha 1 rho V1 squared plus rho G Z1 delta P pump equals P2 plus 1/2 alpha 2 rho V2 squared plus rho G Z2 plus the frictional losses. So when I write this equation like this, which of the assumptions in Bernoulli's equation, the original one, have been relaxed, and which still apply? Yep, the one about external work, right? So what makes you say that? Because we have external work. Good observation. So we have external work, so we're not assuming that anymore. In fact, this delta P pump is just some delta P that comes from an external source. Any other assumptions that have been relaxed? Yes. So alpha is a kinetic energy correction factor. So that has to do with sort of I think what you're going for is the streamline assumption has been relaxed. So in a turbulent pipe flow, the flow is very highly turbulent. So as you saw, it's turbulent. So the streamline would look literally something like that, or something like, I don't know, this. So this equation is for the average along the pipe. So even though in a turbulent flow we don't have streamlines that go like this equation is for the average along the pipe, and that's what that alpha is for. So we're now dealing with averages along the pipe. We're not dealing with exact points along a streamline. So that's another assumption that's been relaxed. What's another assumption that's been relaxed? Yep. Yeah, and viscid flow. Right. So we have the losses term. And when we go to look at losses, so you'll notice the Reynolds number doesn't appear in Bernoulli's original equation. There's no Reynolds number. Let me scroll back up. In this equation, there's no Reynolds number, there's no viscosity, so there's no viscous effects at all. So where viscous effects enter in the extended Bernoulli's equation is through here. We have that friction factor. The friction factor depends on the Reynolds number. So the Reynolds number tells us about the amount of just viscosity, forces due to viscosity versus inertial forces in our flow. So that's where viscous forces enter. I think that is all the assumptions that's been relaxed. So there are certain assumptions that still apply to this equation. And in fact, this equation adds an additional assumption that's we have fully developed flow. Okay. So I've written here the units of this equation. So every term in this equation has units of pascals. So that's kind of pressure form. We also can write it in head form. So we just do everything over rho g. So delta P pump over rho G is just a pump head. And so what are the units of the head form of Bernoulli's equation? Length, meters, yeah. Yeah, exactly. Meters. Yeah. So alpha is the kinetic energy correction factor. So alpha is 2.0 for laminar flows. 1.05 for turbulent flows. Now you might have noticed for your project, if you have a constant diameter pipe, even it's going over terrain, it has frictional losses, it might even have a pump in it. But if you have a constant diameter pipe, these terms cancel because our velocity is the same at both points along that pipe. So the term in here is really about we've caused some sort of difference or conversion to kinetic energy in the flow. So if we're not changing the kinetic energy at any point along the pipe, it always is alpha v squared over, sorry, the kinetic energy would be 1/2 alpha rho v1 squared. So if we're not changing that kinetic energy between 2 points in the pipe, we've just converted pressure basically between elevation and static pressure, or the other way around. So that's why you get in a straight pipe, the static pressure will just go down with sort of length. Okay, the delta P losses. So we need to sum the major and minor losses. Okay, and that's equal to this sum here. So F is the friction factor. Major losses are F, L over D, rho v average squared over 2. We can collect basically these two terms into this form where it's commonly written as. Okay, so that's basically these are both non-dimensional coefficients, right? So F is non-dimensional, L over D is non-dimensional, and KL is non-dimensional. We're saying here that the pressure loss due to frictional effects is some non-dimensional coefficient times the kinetic energy, or sort of the kinetic energy in our pipe. So this is the major losses, and this is the minor losses coefficients. Yep. Yep. I guess I'm not going to say if that's going to be on the exam. So I'm not going to tell you whether or not that part will be on the exam. Okay. So, sorry, the question Aaron asked was there's an equation, right? So this alpha is given as it's an integration. So that equation was given before. So it depends on the kinetic energy and the velocity profile. And yeah, I guess that's getting a little bit too much to is this going to be on the exam or not? So that's definitely part of how we extend Bernoulli's equation to internal flows. Okay, so F here is a function of relative roughness, epsilon over D. So that's a material property, roughness of the inside of the pipe, and the Reynolds number based on diameter. And again, just a reminder, so epsilon will be provided, or I'll give you a table for it in the exam. KL also came from a table when we analyzed it, but those will be provided in exam. Okay, just a reminder, epsilon over d is the relative roughness. Okay, any questions? Okay, I'm going to do one more concept and then give you some time for the survey. So the last thing we talked about in internal flows was flow rate measurement. So remember, the rough idea behind flow rate measurement was that if we know already the loss coefficient of something and we measure the pressure drop across something, we can determine the velocity. So if you have, I'm going to erase this, but I just want to keep this. So if you have something where those slashes are kind of a something in your pipe, and you know the pressure difference here, and you know this thing has a certain loss coefficient, the minor losses are just KL rho V squared over 2. So if you know delta P, you can get the velocity. So we have an equation that I gave for two different types of restriction flow meters. So V dot is A0 CD square root of 2 P1 minus P2 over rho 1 minus beta to the 4. D0 is pi over 4d squared. Beta is the ratio of the diameters. So lowercase d is the restriction diameter. Uppercase D is the pipe diameter. And that CD is not equal to KL. So it's not the same thing as KL. So CD is 0.61 for an orifice plate, 0.98 for a venturi. So if you recall what these two different things look like, you would expect the orifice plate to have a much higher loss because an orifice plate is just an obstruction like this placed in the flow. So the flow goes and it swirls around that plate, and then it continues on down the pipe. The venturi is a really nice sort of restriction. So there's less separation and less pressure loss from a venturi. The other thing that makes CD different than KL is this is the local delta P. So the delta P here is right at that restriction. So if you remember that video I showed, they have pressure taps on either side of the orifice plate. They measure the local pressure differential. Remember that KL is about what is the actual energy that we lost from this fitting. So KL is after the pressure kind of recovers. It's the energy that was lost due to that fitting. That's loss coefficient. Okay. Any questions on the flow rate measurement? Okay. So that's the end of the internal flows part. So I'm going to give you, like I said, some time to work on that survey today. So I have also the review of the conservation laws. So next lecture, I probably have time for one or two examples. I'll pick one if I don't hear from anyone, but if you guys have any specific examples or concepts that you want me to do an example of, then I can do those.